Hello and welcome to the Chemistry Academy. In this video we're going to be looking at the electron configurations for transition metals and talking a bit about transition metal oxidation states. If you are looking for help with electron configurations, I do have another video that looks at how electron configurations are put together for all the elements, not just the transition metals, so that's a good place to start if your fundamental knowledge of electron configurations is lacking. And if you are looking for transition metal complexes, it won't be in this video. If you go and try and find my video on transition metal complexes, that'll be covered there because it's too much for one video. So if we get started on our introduction to transition metals, the transition metals are the elements that are in the D block of the periodic table. So hopefully you know that the D block is this middle block here that I've coloured in green. And when we talk about the D block, what that means is essentially what the outermost filled or atomic orbital is. However, if you do remember from the basic electron configurations, when we are populating electrons and putting them into atomic orbitals, we do so in order of increasing energy, which complies with the Aufbau principle. So when we are initially populating and adding the electron configurations in, we are told that the 4s has to go in before 3d, even though the 4s should be in the fourth shell and 3d is in the third shell. But the reason for that is because before there's any electrons in them, the 4s orbitals are lower in energy than the 3d orbitals. So if we're talking about order of increasing energy, your 4s would be here and the 3d ones would maybe be slightly higher up here. So when the electrons are populating the orbitals, they go into the two go into the 4s atomic orbital first. However, once you start putting electrons into the d orbitals, of which there are 5, those energies then switch. So once there's electrons in the 3d orbital, they actually end up lower in energy than the 4s. So what happens is we get this occurring. This doesn't really affect the populating of the electrons because the 4s electrons are already in there, they're not moving, so we still just keep filling up the 3d. However, what it does affect is the electron configurations of the transition metals. So once the electrons are in the 3d, the 3d is actually written before 4s. So this always gets a bit confusing, but I just like to think of it that until there are electrons in the 3d orbital, the 4s orbitals are lower in energy. Okay, so the 4s electrons go in first, and then you start putting them in the 3d. Once electrons start populating the 3d orbitals, that's when they switch in energy, and your 3d then get written before the 4s in the electron configuration. The other thing this then affects is when the transition metals go on to form ions, the electrons in the 4s orbitals come out before the ones in the 3d because they're higher in energy. So if this atom is going to be ionized, that electron would come out first, followed by that one, and then followed by the 3d one. Okay, so if we look at some examples to put this into practice, we look at scandium first of all. So it's element number 21, and the way that I quite often help myself work out the electron configurations is just by looking up the data booklet. So scandium is the first element in the D block, which tells me that its electron arrangement is going to finish at 3d1. So everything would be filled up until 3d1, including the 4s, because we have the s or atomic orbitals in the fourth period, we've passed them. So we have 1s2, 2s2, 2p6, 3s2, 3p6, and then we shoot the 4s2, then electrons go in, and then we have the 1 in 3d. However, when we're writing the electron configuration of this element in its ground state, we need to swap them around, because like I said, once there's a d electron, 3d electrons in there, the energies swap, and now then the 4s is actually higher than the 3d. So all you need to do is remember to swap that around. Then doing a box notation for the d orbitals, there is just one in there. Okay. You can then do this for any element. So let's do another one as an example. So we'll do iron, which is element number 26. The other thing you can do is just know how many electrons you need and just count them up as you go through the electron configuration, but it does take a bit longer. So if we look at iron, it's 1, 2, 3, 4, 5, 6 boxes along the D block. So that means it's going to end in 3d6. So then the rest of the electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and then 4s2. And in terms of its then box notation, we have 1, 2, 3, 4, 5 populating in degenerate orbitals with parallel spins as per Hund's rule, and then the sixth one will pair up with that there. Okay, so straightforward as that. You just really need to remember that although the 4s electrons go in first, once there's electrons in the 3d subshell, the energies switch, and so for writing the electron configuration of the element in its ground state, you need to put the 3d before the 4s, even though the 3d is not filled. So it does look a bit strange, because remember, you can get 10 electrons altogether in a D subshell. I just wanted to highlight also these two transition metals here, chromium and copper. So these are outliers in terms of obeying the Aufbau principle. So based on the Aufbau principle, where the electrons occupy atomic orbitals in order of increasing energy, the chromium should finish with 3d4, because it's 4 squares into the D block. If we say that it ends in 3d4, I'll put the 4s2, 4s2, and instead of writing all of these, I'm just going to write argon because it's shorter, and all of this basically part of the electron configuration is the same as what argon's is. So in your exam, don't do that. You have to write out the full thing, but I'll just write this for the sake of making it a bit shorter. So in 3D, for the box notation, we'd have 1, 2, 3, 4. However, there is such a thing as half and full orbital or shell stability. So because it's more energetically stable to have a half-filled 3D subshell, what happens is an electron comes out of the 4s and goes into the 3D to make it half-filled, because the half-filled shell is more stable than the partially filled shell. So that's chromium as the first outlier in terms of the Aufbau principle. The next one is copper. So copper is 9 boxes along on the D block, so it should be 3d9. So its electron configuration shortened down should be argons followed by 3d9 and 4s2. So that'd be 1, 2, 3, 4, 5, singly occupying degenerate orbitals with parallel spins as per Hund's rule, and then 6, 7, 8, 9. But again, a full or half-filled subshell orbital is more stable than a partially filled one. So again, what happens is an electron comes out of the 4s and goes into the 3d to make that complete. So these are just two to flag. So maybe you might want to put like a little asterisk next to them on your periodic table, just so you remember that they are anomalies in terms of their electron configurations, and that they only have one electron in the 4s, because one comes out of the 4s and goes into 3d to give you the half or full orbital stability. Okay, so we're going to go and have a look at the oxidation states and the electron configurations of some of the ions now. So looking at oxidation states, oxidation Looking at oxidation states, the oxidation state of an element or an atom is essentially how many electrons has it gained or lost. So if you remember from Nat 5, oxidation is lost. So the more electrons that have been lost, the higher the oxidation state will be for that atom. Non-metals have oxidation states as well as metals, but you'll often find that non-metals have oxidation states that are negative numbers, so negative oxidative numbers. But if we have a look at the examples I've got here, transition metals can adopt a variety of oxidation states, so they are quite flexible in what their charges as ions can be. However, the non-metal atoms or groups of atoms are not flexible in their oxidation states, which means the oxidation state of the transition metal is usually determined by what is attached to it. So you would have done some of this sort of stuff in National 5 and higher when you're asked what the charge of a metal ion is in a given compound. It's the same thing, because the oxidation state is essentially telling you what the charge is. It's just assigning a more official number to it. So if we look at this first example, we've got copper oxide. We should know from National 5 that as an ion, oxide is always a 2 negative charge. Okay, so if we have one oxygen here with a 2 negative charge, that means it's taken 2 electrons off this copper, and the copper has to balance that. So this means those coppers altogether have to be, this side is 2 minus, this side has to be 2 plus. Now there's 2 copper ions, which means that 2 positive charge is shared between both of them. So that leaves each of the copper in a 1 positive oxidation state, meaning its charge is a single positive charge. So the oxidation number, or the oxidation state for copper in this compound is 1 positive. This means that this compound would be called copper 1 oxide, because the copper is in the oxidation state of 1. And that's what the Roman numeral essentially tells us, and the name is the oxidation state of the metal. If we go into this example here, the manganese, if we find the oxidation state of that, so again, I'll kind of split this in half. We know that oxygen always has 2 negative as a charge, so altogether that would be an 8 negative. Okay, we're going to ignore this negative sign here for just now. That means then that manganese would have to be 8 positive to balance that out. But this extra negative charge here is like adding an extra electron back on. So these oxygens, 4 of them, took 8 electrons away from the manganese, but this extra negative charge is like adding 1 back on. So then that would change the oxidation number to 7 positive for the manganese. Okay. If we go on to this example here, 7 oxygens, that would be 14 electrons being removed from the chromiums. However, with this 2 negative charge, you're essentially adding 2 back on. So 14 take away 2 means that would be 12 electrons being removed from the chromiums. So that gives us the 12 positive on the other side. There's 2 chromiums there, so we divide that positive charge by 2, which means that each chromium has lost 6 electrons, giving its oxidation number of 6. Okay, so the chromium here has got an oxidation number of 6, positive or plus 6. One last example here. Chloride ions, they will take 1 electron off the metal because they have a 1 negative charge. Hopefully you'll remember that from National 5 as well. So if there's 2 of them, that's like taking 2 electrons off, which means that the cobalt will be in a 2 positive oxidation state. Okay, so it's really as straightforward as seeing how many electrons the non-metal groups are taking off the metal. If there's any overall charges, then it's like adding electrons back on. And if you've got more than 1 metal ion, just make sure that you share the electrons that have been taken off between them, because it's not all just going to be taken off one of the metal ions, it's both of them. So the oxidation state for cobalt here is 2 positive. Okay. What we're going to do now then is look at, based on the oxidation state, then what, or the charge of the ion, what then its electron configuration would be. So if we just pick a couple of these examples, so we'll just do the cobalt since it's got a bit more space underneath it. So the cobalt we've worked out has got an oxidation state of 2 positive. That means that it is cobalt 2 plus. Cobalt's electron configuration normally would be, if we look at how many boxes into the 3D row is, so it's 1, 2, 3, 4, 5, 6, 7. So it should be 3D7 with the 4s2 before it. So again, I'll just use the argon shorthand. So it should be 3D7 4s2. As a, that would be for cobalt, just as a atom. However, it's lost 2 electrons, and like I said before, although the 4s electrons go in first, they also come out first. So we don't take any of the d electrons away, it would be the 2 4s electrons that would be removed. So therefore, the electron arrangement for cobalt 2 plus would be argon's electron arrangement or electron configuration plus the 3d7. If we then look at chromium, so chromium we worked out was in a 6 positive state, so that means it's Cr6 plus. As an ion, chromium's electron configuration should normally be, it's 4 boxes into the 3D, so it should be argons with then 3d4 and 4s2. It's lost 6 electrons, the 4s ones come out first, so those 2 come out, and then we also take out all of the 4 3D ones too. So the electron configuration for chromium 6 positive is just that of argon, so I'll write that out fully. So 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and we'll do one more example. So let's do copper 1 to finish off. So Cu plus. So if we look at copper, it is 1, 2, 3, 4, 5, 6, 7, 8, 9 into the D block. And remember, copper has got the electron arrangement that doesn't fit the Aufbau principle because it's got that full shell stability, so it doesn't have a full, it only has one 4s electron, and then it has the full D subshell. So in a 1 positive state, sorry, the 4s electron comes out first, so then that would be the electron configuration for copper plus. If we had copper 2 plus, which you can get as well, then we would just be taking then out a D electron, so then it would end up as 3d9. Okay. You can also get asked questions about ionic stability. So if we were to compare the stability of these 2 copper ions, if we look at the box notation of both of them, so these are the 3D subshells. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in terms of which one's more stable, the copper positive will be more stable because it has a full 3D subshell, which again is more stable than if it was partially filled. The same happens often with iron ions, iron 2 versus iron 3. One of them has got half box stability or half orbital stability, the other one doesn't. So the ions that have full subshell or half subshell stability are the more stable ions. Okay, so you can be asked about that sometimes as well. Okay, so we'll finish off by looking at iron 2 and iron 3. So iron 2, iron 3. Iron should be 1, 2, 3, 4, 5, 6. So it should be 3d6. And then 4s, I can't write, and then 4s2. So that's what iron is. So then when it's iron 2, those come out. 4s ones, and then iron 3 then will have one of those 3d electrons taken away. So it'd be 3d5. So then if we do our 3d orbitals in the box notation, so iron 2's got 6, so 1, 2, 3, 4, 5, 6, and then iron 3's got 5, 1, 2, 3, 4, 5. So you can see the iron 3 has half box or half orbital stability, so it will be the more stable ion. So if you're asked anything about ion stability, have a look at the box notation and see if you can see any half-filled subshells or fully filled subshells. So hopefully that helped you get your head a little bit around transition metals and how to write their electron configurations and work out their oxidation states. The oxidation states does really just take a little bit of practice, but it is essentially using your National 5 knowledge of the ion charges. So look for what the non-metal groups are, work out how many electrons they need to take to become stable, because that's why they're bonding in the first place, and then any positive charges just share, or electrons that have been removed, just share it between any metal atoms that are there. If you found this video helpful, please give it a like, don't forget to subscribe, and I'll see you again soon.